This episode is brought to you by Cisco Educational Premium. The Planck unit of force may be thought as the derived unit of force in the Planck system if the Planck units of time, length, and mass are considered to be the base units. It is the gravitational attractive force of two bodies of one Planck mass each that are held one Planck length apart. One convention for the Planck charge is to choose it so that the electrostatic repulsion of two objects with Planck charge and mass that are held one Planck length apart balances the Newtonian attraction between them. Some others have argued that Planck force is on the order of the maximum force that occurs between two bodies. However, the validity of these conjectures has been disputed. The Planck temperature Tp is 1.41678416 times 10 raised to 32 Kelvin. At this temperature, the wavelength of light emitted by thermal radiation reaches the Planck length. There are no known physical models able to describe temperatures greater than the Planck temperature. A quantum theory of gravity would be required to model the extreme energies attained. Hypothetically, a system in thermal equilibrium at the Planck temperature might contain Planck-scale black holes, constantly being formed from thermal radiation and decay via Hawking evaporation. Adding energy to such a system might decrease its temperature by creating larger black holes whose Hawking temperature is lower. Physical quantities that have different dimensions such as time and length cannot be equated even if they are numerically equal. Like 1 second is not the same as 1 meter. In theoretical physics, however, this problem may be set aside by a process called non-dimensionalization. The effective result is that many fundamental equations of physics, which often include the sum of the constants used to define Planck units, become equations where these constants are replaced by 1. Examples include the energy momentum relation becomes E square is equivalent to C square bracket all of that raised to 2 plus PC square, which become E square is equivalent to M square plus P square, and the Dirac equation which evolved, which becomes as shown. As we have already looked at, Planck units are derived by normalizing the numerical values of certain fundamental constants to 1. These normalizations are neither the only ones possible nor necessarily the best. However, the choice of what factors to normalize among the factors appearing in the fundamental equation of physics is not evident, and the values of Planck units are sensitive to this choice. The factor 4 pi is ubiquitous in theoretical physics because in 3-dimensional space, the surface area of a sphere of radius r is 4 pi r square. This, along with the concept of flux, are the basis for the inverse square law, Gauss law, and the divergence operator applied to the flux density. For example, gravitational and electrostatic fields produced by point objects have spherical symmetry, and so the electric flux through a sphere of radius r around a point charge will be distributed uniformly over that sphere. For this, it follows that a factor of 4 pi r square will appear in the denominator of Coulomb's law in rationalized form. Both the numerical factor and the power of the dependence on r would change if space were higher dimensional. The correct expression can be deduced from the geometry of higher dimensional spheres. Likewise, for Newton's law of universal gravitation, a factor of 4 pi naturally appears in Poisson's equation when relating the gravitational potential to the distribution of matter. Hence, a substantial body of physical theory developed since Planck's 1899 paper suggests normalizing not g but 4 pi g or 8 pi g to 1. Doing so introduced a factor of 1 on 4 pi or 1 on 8 pi into non-dimensionalized form of the law of universal gravitation, consistent with the modern rationalized formulation of Coulomb's law in terms of vacuum permittivity. In fact, alternative normalizations frequently preserve the factor of 1 on 4 pi in the non-dimensionalized form of Coulomb's law as well, so that the non-dimensionalized Maxwell's equation for electromagnetism and gravitoelectromagnetism both take the same form as those for electromagnetism in SI, which do not have any factors of 4 pi. When these apply to electromagnetic constants E0, this unit system is called, and I quote, rationalized. When applied additionally to gravitation and Planck units, these are called rationalized Planck units and are seen in high energy physics. The rationalized Planck units are defined so that C is equivalent to 4 pi g, which is equivalent to reduced Planck's constant, which is equivalent to E0, which is equivalent to Kb, which is equivalent to 1. There are several possible alternative normalizations. In 1899, the Newton's law of gravitation was still seen as exact, rather than as a convenient approximation, holding for an accord small velocities and masses. The approximate nature of Newton's law was shown following the development of general relativity in 1915. Hence, Planck normalized the gravitational constant g in Newton's law. In theories emerging after 1899, g nearly always appears in formulae multiplied by 4 pi or a small integer multiplied thereof. Hence, a choice to be made when designing a system of natural units in which, if any, instances of 4 pi appearing in the equations of physics are to be eliminated for the normalization. 1. Normalizing 4 pi g to 1 and therefore setting g to be equivalent to 1 on 4 pi. Whose law for gravity becomes phi g, which is equivalent to negative 4 pi m in Planck units. Something else is that it eliminates 4 pi g from the Poisson equation. Also, it eliminates 4 pi g in the gravitoelectromagnetic GM equation, which hold in weak gravitational fields or locally flat space-time. These equations have the same form as Maxwell's equations and the Lorentz force equation of electromagnetism, with mass density replacing charge density and with 1 on 4 pi g replacing epsilon naught. It normalizes the characteristic impedance Zg of gravitational radiation in free space to 1, normally expressed as 4 pi g on C. It also eliminates 4 pi g from the Bekenstein-Hawking formula for entropy of a black hole in terms of its mass, mbh, and the area of its event horizon, abh, which is simplified to SBH is equivalent to pi, ABH is equivalent to mbh square. 2. Setting 8 pi g to be equivalent to 1, and therefore setting g to be equivalent to 1 on 8 pi. This would eliminate 8 pi g from the Einstein field equations, Einstein-Hilbert action, and the Friedmann equation for gravitation. Planck units modified so that 8 pi g will be equivalent to 1 are known as reduced Planck units, because the Planck mass is divided by root 8 pi. Also, the Bekenstein-Hawking formula for the entropy of a black hole simplified. This episode is brought to you by Cisco Educational Premium.
Atoms and molecules are consistently in motion, colliding, twisting, and spinning, resulting in a chaotic scenario. However, one thing becomes evident: atoms lack a definite boundary. They exist a nucleus, a collection of protons and neutrons at the center, surrounded by clouds of probabilities that indicate the potential locations of orbiting electrons. The principles of quantum mechanics allows us to calculate probabilities which extend through the entire universe. Nevertheless, in nearly all observations, electrons remain securely bounded to the nucleus. So unless we are conducting high-energy collider experiments, we don't have to worry too much about it. Since atoms lack a firm surface in a way, there's no tangible touch because there is never a direct meeting of the boundaries. However, touch also implies close and influential interaction, and in that sense, atoms are in constant contact. Atoms interact due to the electromagnetic force which arises from the electric charges of the protons and electrons within them. Technically, this force has an infinite range, but it becomes significant only when atoms are significantly close. At times, atoms literally repel each other due to the electromagnetic force between their electrons. In their brief movement, it is challenging to describe their interaction as anything but touching. Even if the interaction is not momentarily, it still qualifies as touching. For instance, when we examine the palm at the chair, at the atomic and molecular level, we notice that the electrons at the palm outer edge are repelled by the electrons on the chair's outer edge. Despite the gap within the layers of electrons which typically exist, the atoms are close enough to significantly influence each other. This is evident from the fact that the cup does not fall through the chair, and the electromagnetic forces between the atom counteract the gravity's pull of the cup. At the microscopic scale, when we say two objects are touching, it reflects the same interaction at the microscopic level. Atoms can also touch through other means. As electromagnetic force is not always repulsive, when atoms get close, the van der Waals force, the manifestation of the electromagnetic force, can lead to bonding between atoms. This process results in the formation of molecules, where the atoms inside them are definitely in contact. Lastly, even nuclei within atoms can touch, although it is extremely difficult due to the strong electromagnetic repulsion between the positively charged protons in each nucleus. Yet quantum mechanics play a role here too. If two atoms are brought close enough and maintained for sufficient time, occasionally and randomly, their nuclei can intermingle. This phenomenon leads to nuclear fusion, where two separate atoms merge into a single larger atom. If the atoms involved are lighter than iron, the fusion process releases energy. It is through this mechanism that all stars, including our sun, generate their power. Two atoms of the same element are typically non-distinguishable. First, electrons in an atom can occupy a range of possible states. Therefore, two atoms of the same element can be different if their electrons occupy a different state. For example, one copper atom with an electron in an excited state and another copper atom with all electrons in the ground state are distinct. The excited copper atom will emit light when the electron returns to the ground state, while the copper atom in the ground state will not. The nature of the chemical bonding experienced by an atom depends on the state of its electrons, so two atoms of the same element can react differently if they are in different states. We chemists are aware of this fact, and to fully describe and predict a reaction, it is necessary to specify excitation states of the electrons in the atoms. Additionally, even when left alone, an atom often does not have an equal number of protons and electrons. However, even if two atoms of the same element have their electrons in the same state, they are still not identical. For example, they could be traveling or rotating at different speeds, which influences their ability to chemically bond. Slow moving atoms, such as those in solid iron, have time to form stable bonds, whereas faster moving atoms, like those in liquid iron, cannot establish such stable bonds. As a result, a slow moving thin atom is different from a rapid moving thin atom. But what if two atoms of the same element both have their electrons in the same state? and the atoms are both traveling and rotating at the same speed, then are they indistinguishable? No. Although two such atoms are essentially chemically identical, they will chemically react in the same way. They are chemically identical. Beyond the electrons, there is also the nucleus to consider. An atom's nucleus contains tightly bonded neutrons and protons. The same chemical element can have different number of neutrons and still be the same element. These atoms with different number of neutrons are referred to as isotopes. While a particular isotope involved does not impact an atom's chemical reactions, it does determine how an atom behaves in nuclear reactions. Radioactive decay, the most common nuclear reaction on Earth, varies among different isotopes. Some isotopes decay rapidly into other elements in a mid radiation, while others do not. For carbon dating, the fact that carbon-12 is not the same as carbon-14 atom is crucial to the dating process. Simply counting the number of carbon atoms in a sample will not provide information about the sample's age. Instead, you have to count the number of different isotopes of carbon. But what if two atoms are of the same element, have electrons in the same state, and traveling and rotating at the same speed, and have the same number of neutrons? Then are they indistinguishable? No. Just like electrons, the neutrons and protons in the nucleus can exist in the various excited states. Additionally, the nucleus as a whole can rotate and vibrate at different speeds. And even if all else is identical, two gold atoms can have their nuclei at different excited states and behaves differently in nuclear reactions. In summary, achieving two atoms of the same element to be perfectly identical is exceedingly difficult. In fact, such an accomplishment will be a Nobel Prize worthy. Nevertheless, it is important to note that atoms do not possess individual identities beyond what has been mentioned here. If two carbon atoms are in the exact same molecular, atomic, electronic, and nuclear state, then those two carbon atoms are identical regardless of their origin or past history. Everything has color. Since almost everything have color, atoms as the fundamental building blocks of reality should also have color. Or does it? When you aggregate numerous atoms together, you obtain the screen that you are constantly observing, which indeed has color. So, does it imply that each individual atom has its own color as well? If so, is it the nucleus or electrons that are painted? And if so, what color? The color we perceive are a creation of the human brain. They don't actually exist outside our visual perception. So then, what precisely is color? To understand this, we need to comprehend the nature of light. Light consists of photons, which are particles. However, this behavior is only evident when observed. Otherwise, they tend to act as electromagnetic waves. This phenomenon is known as the wave-particle duality concept. And yes, it is peculiar. These waves possess specific frequencies, and depending on their frequencies, they are classified to 7 primary wavelength sections. Ranging from radio waves with wavelengths the size of Earth to gamma rays the size of atoms.
This episode is brought to you by Cisco Educational Premium. Units such as those of time and length are many orders of magnitude too large or too small to be of practical use, so that Planck units as a system are typically only relevant to theoretical physics. In some cases, a Planck unit may suggest a limit to a range of physical quantity where present-day theories of physics apply. For example, our understanding of the Big Bang does not extend the Planck epoch. That is, when the universe was less than 1 Planck time old. Describing the universe using the Planck epoch requires a theory of quantum gravity that will incorporate quantum effects into general relativity. Such a theory does not yet exist. Several quantities are not, and I quote, extreme in magnitude, such as the Planck mass, which is about 22 micrograms, very large in comparison with subatomic particles and within the mass range of living organisms. Similarly, the relative units of energy and momentum are in the range of some everyday phenomena. Planck units have little anthropocentric arbitrariness, but do still involve some arbitrary choices in terms of the defining constants. Unlike the meter and second, which exist as base units in the SI system for historical reasons, the Planck length and Planck time are conceptually linked at a fundamental physical level. Consequently, natural units help physicists to frame questions. Frank Wilczek puts it succinctly. We see that the question is not why is gravity so feeble, but rather why is the proton's mass so small? For natural Planck units, the strength of gravity simply is what it is, a primary quantity, while proton's mass is the tiny number 1 on 13 quintillion. While it is true that the electrostatic repulsive force between two protons alone in free space greatly exceeds the gravitational attractive forces between the same two protons, doesn't about the relative strength of the two fundamental forces. From the point of view of Planck units, this is comparing apples with oranges because mass and electric charge are incommensurable quantities. Rather, the disparity of magnitude of force is a manifestation of the fact that the charge on the proton is approximately the unit charge, but the mass of the protons is far less than the unit mass. In particle physics and physical cosmology, the Planck scale is an energy scale around 1.22 times 10 raised to 19 gigafolds. The Planck energy corresponding with the energy equivalent of the Planck mass is 2.17645 times 10 raised to negative 8 kilogram, at which quantum effects of gravity become significant. At this scale, present description and theories of subatomic particle interactions in terms of quantum field theory break down and become inadequate due to the impact of the apparent non-renormalization of gravity within current theories. At the Planck scale, the strength of gravity is expected to become comparable with the other forces, and it has been theorized that all the fundamental forces are unified at that scale. But the exact mechanism of this unification remains unknown. The Planck scale is therefore the point at which the effects of quantum gravity can no longer be ignored in other fundamental interactions, where current calculations and approaches begin to break down and a means to take account of its impact is necessary. On these grounds, it has been speculated that it may be an appropriate lower limit at which a black hole could be formed by collapse. While physicists have a fairly good understanding of the other fundamental interactions of forces on the quantum level, gravity is problematic and cannot be integrated with quantum mechanics at very high energies using the usual framework of the quantum field theory. At lesser energy levels, it is usually ignored, while for energies approaching or exceeding the Planck scale, a new theory of quantum gravity is necessary. Approaches to this problem include string theory and M theory, loop quantum gravity, non-commutative geometry, and causal theory. In Big Bang cosmology, the Planck epoch or the Planck era is the earliest stage of the Big Bang before the time passed was equal to the Planck time, or approximately 10 raised to negative 43 seconds. There is no current available physical theory to describe such short times, and it is not clear In what sense the concept of time is meaningful for values smaller than the Planck time? It is generally assumed that quantum effects of gravity dominate physical interactions at this time scale. At this scale, the unified force of the Standard Model is assumed to be unified with gravitation. Immeasurably hot and dense, the state of the Planck epoch was succeeded by the Grand Unification epoch, where gravitation is separated from the unified force of the Standard Model, in turn followed by inflationary epoch, which ended after about 10 raised to negative 2 seconds, or about 10 raised to 11 Planck time. After the measurement of the cosmological constant in 1998, estimated at 10 raised to negative 122 in Planck units, it was noted that this is suggestively close to the reciprocal of the age of the universe squared. Barrow and Shaw propose a modified theory in which the cosmological constant lambda is a field evolving in such a way that its value remains lambda equivalent to the age of the universe squared through the history of the universe. The Planck length, denoted Lp, is a unit of length defined as Lp is equivalent to root of reduced Planck constant G on C raised to 3. It is equal to 1.6162518 times 10 raised to negative 45 meters, where the two digits enclosed by parentheses are estimated standard error associated with the reported numerical value, or about 10 raised to negative 20 times the diameter of a proton. It can be motivated in various ways, such as considering a particle whose reduced Compton wavelength is comparable to its Schwarzschild radius. Though whether those concepts are in fact simultaneously applicable is open to debate. The same heuristic argument simultaneously motivates the Planck mass. The Planck length is a distance scale of interest in speculation about quantum gravity. The Bekenstein-Hawking entropy of a black hole is 1/4 area of its event horizon in units of Planck length squared. Since 1950s, it has been conjectured that quantum fluctuations of the space-time metric might make the familiar notion of distance inapplicable below the Planck length. This is sometimes expressed by saying that, and I quote, space-time becomes a form at the Planck scale. It is possible that the Planck length is the shortest physically measurable distance, since any attempt to investigate the possible existence of shorter distances by performing high energy collision would result in a black hole production. High energy collision, rather than splitting matter into finer pieces, would simply produce bigger black holes. The strengths of string theory are modeled to be on the order of the Planck length. In theories with large extra dimensions, the Planck length calculated from the observed value of G can be smaller than the true fundamental Planck length. The Planck time, Tp, is the time required for light to travel a distance of 1 Planck length in a vacuum, which is a time interval of approximately 5.39 times 10 raised to negative 44 seconds. No current physical theory can describe time scale shorter than the Planck time, such as the earliest events after the Big Bang. Some conjecture that the structure of time need not remain smooth at intervals comparable to the Planck time. The Planck energy EP is approximately equal to the energy released in the combustion of the fuel in automobile fuel tank, 57.2 liters at 4.2 megajoule per liter of chemical energy. The ultra-high energy cosmic ray observed in 1991 had a measured energy of about 50 joules, equivalent to about 2.5 times 10 raised to negative 8 Planck energy. Proposal for theories of doubly special relativity posit that in addition to the speed of light, an energy scale is also invariant for all inertial observers. Typically, this energy scale is chosen to be the Planck energy. This episode is brought to you by Cisco Educational Premium.
Epoch of the universe known as the Planck epoch occurred at 10 raised to negative 43 seconds. During this time, it is believed that all the fundamental forces, including electromagnetism, the weak force and the strong force, were unified as one grand unified force at this point. However, it is important to note that this isn't exactly t is equal to 1, as we want to avoid the singularity. The state of the universe at this epoch and what happened before it remain unknown. The earliest time we can theorize about is the period of inflation, which occurred from about 10 raised to negative 36 seconds to about 10 raised to negative 33 seconds after the Big Bang. During this time, whatever existed prior to inflation experienced rapid exponential expansion, faster than the speed of light. This is allowed because there is no theoretical restriction on the speed at which space itself can expand. It expanded from a point to a point about the size of a baseball. You might wonder how this is even possible since we know that nothing can travel faster than the speed of light. While this is true for information transfer, cosmic inflation involves the expansion of space itself, allowing distant points to move away from each other faster than light can travel between them. Most of our current understanding comes from the period after inflation. So the accurate way to view the Big Bang is not as a single point of origin, but as a period when the early universe was extremely hot, dense and rapidly expanding. Thus the Big Bang is a description of everything that occurred after t is equal to 1. Inflation is believed to have occurred from 10 raised to negative 36 to 10 raised to negative 3 seconds. The energy source behind this rapid expansion and cosmic inflation erased any information about what existed before it. The theory of the standard model of cosmology is well understood, starting at about 10 raised to negative 12 seconds, as the universe's energy levels can be reproduced in current particle accelerators. Before this time, we can only speculate about the events. From about 10 raised to negative 3 seconds to 10 raised to 12 seconds, strong force and electromagnetic and weak forces, collectively known as electroweak force, was still unified. The origin of the initial massless fundamental particles is uncertain. They might have condensed from the energies present during the Big Bang, or an inflation field containing inflations could have decayed into the fundamental particles we observe today. Around 10 raised to negative 11 seconds, the temperature drops further to 10 raised to 15 Kelvin, marking the beginning of the quark epoch. The electromagnetic and weak forces begin to separate, leading to electroweak symmetry breaking. The X-fields gains a non-zero potential, imparting mass to the fundamental particles of the standard model. At this point, the essential components of atoms are in place, and the universe temperature is around 1 quadrillion Kelvin. As the universe continues to expand and cool, the extremely high temperatures present prevent quarks from combining into hadrons like protons and neutrons. However, as temperature drops to about 1 trillion Kelvin at 10 raised to negative 5 seconds, the quark plasma transitions into a hadron gas consisting of protons, neutrons, and certain mesons, which eventually decay into photons and electrons. As the temperature further decreases, particles and antiparticles begin to annihilate, resulting in lighter particle-antiparticle pairs, such as neutrinos and photons. Interestingly, there is a slight asymmetry in this process, which with more particles being generated than antiparticles, leading to the survival of certain quarks and electrons. This enables the formation of protons, neutrons, and electrons, which are essential for creating the initial atoms. The annihilation process culminates with the Lipton epoch, which occurs around 1 second mark when the temperature subsides to about 5 billion Kelvin. During this epoch, leptons conclude the annihilation process. Following this remarkable display, the majority of the matter particles transforms into photons and neutrinos. However, due to the matter antimatter asymmetry, a small quantity of protons, neutrons, and electrons remain surviving as the fundamental building blocks for atoms. At around a few minutes after the universe's inception, the epoch of the Big Bang nucleosynthesis (BBN) begins with protons and neutrons produced in equal numbers. Free neutrons are inherently unstable and undergo beta decay, transforming into protons over approximately 10 raised to 50 minutes. As the temperature remains high, proton-neutron conversion is balanced by neutron-proton conversion. But as the universe cools further, neutron decay becomes more prevalent. Free neutrons strive to join other hadrons and form more extensive nuclei before decay, leading to the universe consisting of about 75% hydrogen nuclei and 25% helium-4 nuclei, along with small amounts of barium, helium-3, and trace quantities of lithium-9 nuclei. During this period, the environment predominantly consisting of ionized nuclei without bound electrons. The formation of neutral atoms requires electrons to attach to positively charged nucleons to achieve charge balance. However, the universe is still scorching and electrons can only briefly adhere to nucleons before being forcibly separated due to their immense energy. As a result, the universe remains opaque and photons carrying light continuously interact with nucleons and electrons, hindering their free propagation through space. This photon epoch lasts for about 390,000 years until the universe cools down to 3000 Kelvin. At this point, electrons possess significantly reduced energy, allowing the electromagnetic force to permanently bind them to nucleons, leading to the formation of stable neutral atoms in a process called recombination. As a consequence, photons are no longer confined amidst the chaos of positive nucleons and negative electrons. They are now free to traverse the universe. If an observer was present in space, he or she would be able to observe this light. Today, the first light of the universe, known as the cosmic microwave background (CMB), can be perceived in all directions. This light was emitted during the formation of stable neutral atoms, providing us with valuable insights into the early universe and the origin of atoms. Atoms constantly interact. However, to comprehend this, we must first determine the definition of interact. Our typical understanding of interaction is based on the macroscopic world. I place my palm on the chair. My palm interacts with the chair. You step on the floor, you interact with the floor, and so forth. In these instances, one solid boundary or surface interact with another solid boundary or surface. Nevertheless, our macroscopic understanding becomes less applicable at a microscopic level, which leads to confusion about interaction. If we could magnify the scale to atomic level, we would witness a chaotic envisionment.
Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.
Yeah.